So far, we have talked about with with quantitative data, summarizing that data with more numbers, like measures of center, measures of dispersion. One of those measures of dispersion was range, another was the standard deviation. Now we're going to talk about measures of location, and that will not only give us another type of information, but furthermore, one more way that we can measure dispersion. So what I want to talk to you about first is something called a z-score. As a reminder, when you're talking about a population, to find the mean, you add up all the scores and then divide by the number of scores. Well, this sum, remember that's the symbol capital sigma there in front of the X, short for score. If all of these were about pulse rates in beats per minute, then the sum would be in beats per minute. But there wouldn't be any unit for how many. So when you divide a total in beats per minute by something without any unit, then your mean is going to be in beats per minute. Variance, if we're talking about a population, is computed this way. It is simply the standard deviation squared, although usually you would go in this direction from variance to standard deviation. Well, I want you to notice that if the scores and the mean had the same units, then the difference of each score minus the mean would have the same units, in this case, beats per minute. Well, if we square that, whatever beats per minute squared is, the sum is going to be measured that way. Dividing by the unitless n would still give us whatever square beats per minute are, but then taking the square root, our standard deviation, sigma for the population, would be back to being in beats per minute. As a little side note, if you have your information from a sample, you would have x bar instead of mu, and you would have, instead of n, you would have the capital N, you would have lowercase n minus 1. Okay, so what is a z-score? It is a standardized score to take whatever distribution you're working with, whatever the mean and the standard deviation are, and if it's different from 0 for the mean, it's going to shift left or right to make the related distribution have a mean of 0. And if the standard deviation is at 1, then it'll stretch it or compress it by dividing by sigma. Here's how you calculate it. But if it were for sample, then you'd have this. All right, so some examples. Suppose we know that for adult women, the mean pulse rate in the entire population is 77.5 beats per minute, with a standard deviation of 11.6. And we want to take a look at the z-score for a woman with a pulse rate of 91.9 and another woman with a pulse rate of 46.8, and interpret both of those. Now, by the way, the computations typically get rounded to the nearest hundredth, 2 places after the decimal point, and I'll include that when I show the computations. So plugging into the formula, notice how for this first woman, I've subtracted first, then I'm going to divide by 11.6, and then round to the nearest hundredth. On a calculator, if it has parentheses or if it's the TI-84, then you don't have to break it down into 2 steps. You can put parentheses around the 91.9 minus 77.5, and then divide by the 11.6 all at once. This is important because it's not x minus mu over sigma. It's all of square minus mean, x minus mu. All of that is divided by sigma. And so the parentheses are important. And still, when we round to the hundredths place, we get 1.24. Now, interpreting, and then one more example, and interpreting that. Since it's positive, even if I didn't have that initial information, when I see a positive z-score, I know that I'm looking at a score that is bigger than the mean. You should then expect a negative where the raw score is less than the raw mean. And we'll see that in a moment. So that 1.24, that's somewhere between 1 and 2. That means that a woman's pulse rate is more than 11.6 beats per minute above the mean, but less than 2. So it's less than whatever 77.5 plus 2 times 11.6 is. Specifically, it's this far away from the mean in terms of standard deviations. Now, for the woman with a pulse rate of 46.8, again, you could just put parentheses around the subtraction in the numerator and then divide by 11.6 all at the same time. And rounding that, she has a z-score of negative 2.65. So because it's negative, her pulse rate was less than the population's pulse rate on average. If you think about the absolute value here for a moment, then it's more than 2 standard deviations away from the mean, but less than 3 away, and it's below it. So specifically, this is telling us how far below the mean to go in terms of standard deviations.